morning to Dr. Munjal sir, our today's DCP, Dr. R.B. Khasya, Principal of LD College of Engineering, Ahmedabad, respected HODs, faculty members, students, and all the participants. I myself, Professor R.M. Jadhav, Associate Professor in Civil Engineering Department, on behalf of TNA Committee of LDCE, welcome you all for today's expert talk on vibration control in industry by Dr. M.L. Munjal sir. We are very fortunate that today we are very fortunate that Dr. Munjal sir has been nominated as our DCP, that is Distinguished Chair Professor Fellowship by AICTE. I hope you must have attended the previous talks also of this lecture series. Today's our topic is on vibration control in industry. Before going into the depth, I would like to introduce our today's distinguished chair professor, Dr. M.L. Munjal sir. Dr. Munjal sir has obtained his degree in mechanical engineering from Punjab Engineering College, Chandigarh. He has done his master in internal combustion engineering in 1968 and PhD in 1971 from the Indian Institute of Science. He had published over 210 papers in professional journals. He has authored a monograph, Acoustics of Ducts and Muffler, a textbook on noise and vibration control, and contributed chapters in a couple of international handbooks. Dr. Munjal has been remained office bearer of the various institutions like Facility for Research in Technical Acoustics, Institute of Noise Control Engineering of USA, International Institute of Acoustics and Vibration, National Committee for Noise Pollution Control for about 18 years, Acoustical Society of India, etc. He is a fellow of the Indian National Science Academy, Indian National Academy of Engineering, European Academy of Science. He has received several medals and awards during his career. Amongst them, he received Science Academy Medal for Young Scientists in Noise Control and Vehicle Dynamics in 1975, and he has also received Pandit Jawaharlal Nehru Award for the engineering and technology, particularly in noise pollution control in 2010. After his formal retirement in 2010, he was INAE Distinguished Professor during 2010 to 13, Honorary Professor of the Institute from 10 to 15. He was INSA Senior Scientist from 13 to 18, and currently he is a INSA Honorary Scientist at IISc and AICTE Distinguished Chair Professor. We are very fortunate to have such a great personality today with us. I hope all of you will definitely like this session. Before we start further, I would like to introduce our principal, Dr. R.B. Khasya sir. He has about more than 30 years of experience, and right now he is serving as the HOD of the Civil Engineering Department. I would also like to mention here that LD College of Engineering is the only institute to receive 5-star rating by Gujarat State Institution Rating Framework for the year 2021. Also in the year 21, LD College of Engineering ranked 28th amongst India's best engineering colleges by India Today Group. I would request our principal, Dr. R.B. Khasya sir, to share a few words. Over to you, sir.
Good morning to all. As you know, AICTE has selected LD College of Engineering under the AICTE Distinguished Chair Professor DCP Scheme 2021. The AICTE DCP scheme is meant for motivating and inspiring students and faculty members of the AICTE approved institute so as to make them more relevant and effective toward nation building. AICTE has nominated Dr. Manohar Munjal, IIC Bangalore, a highly qualified and experienced professional who have made unparalleled exceptional professional contributions to the society in their respective field. It is our pride privilege that today Dr. Munjal has scheduled an expert talk for the faculty, PG students and senior students. So on the behalf of LT College of Engineering, I welcome Dr. Munjal sir. Thank you sir.
Uh, shall I start now?
Yes, sir, sure. Thank you so much, sir. Now I would like Dr. Munjal, sir, to continue the session. Over to you, sir.
Can you all see the screen, please?
Yes, sir.
Yes, sir. Okay, okay, friends. So thank you very much for your introduction, etc. I must say it's really a pleasure talking to all of you on something that I have been working on for the last 5 decades. In fact, the book that I have written that has also been mentioned in the introduction. It is Noise and Vibration Control in Industry, and it is based on my 5 decades of consultancy experience. In fact, I have done more than 125 consultancy projects both in India and abroad. So I thought when I was called upon by AICTE to give you a general talk, I'll make it semi-technical today, and I'll really briefly tell you what all I have learned regarding vibration control industry. Okay, I'll not go into details of anything, but I'm sure you will be able to appreciate and hopefully use what you get today. So I just called it vibration control in industry, and it is basically extracted. The slides that I'm going to present, they are extracted from chapters 2 and 3 of that book. Now, the unbalanced forces and movements of a reciprocating machinery, like a reciprocating compressor or engine, or rotating machinery like a turbine, not only make the machine vibrate, but are also transmitted in part to the foundation. The oscillating forces so transmitted propagate through the floor or structure-borne sound as structure-borne sound and radiate audible sound elsewhere. Similarly, oscillation of a surface supporting a sensitive instrument may transmit motion to the instrument. These two phenomena are shown in the next figure. You can see here, this is very common. We are, for example, testing an engine or compressor or whatever. This is the mass of the machine. And then we have vibration isolator, and that will be represented by a stiffness spring and then damper. Okay, and not both of them will be explicitly like this, but any viscoelastic layer that we use, that will have both stiffness and the damping. So what happens is that now unbalanced forces act on this mass, and then through this, a part of the force is passed on to this. Similarly, this mass starts vibrating. So we have two the problems. One is the vibration of the mass, which itself may be undesirable, but more than that, the unbalanced forces being passed on to the foundation, which then travel as structure-borne sound to other places and then react and there finally radiate as sound. This is what we call transmission of force. Now, there is another instance, and that is like, for example, you might have instruments on the, let's say, aircraft board, and then those starts vibrating. So it's like that vibration of the support is given, and then we want to make sure that this mass, which may be our meter, that should not vibrate, otherwise the person will not be able to catch the reading. Okay, so here now we have this displacement which we don't want to be transmitted to the mass. Here it was force that we did not want to be transmitted to the foundation. So these are the two cases. We call it transmissibility of force and motion, and I'm going to show you now that they are very similar when it comes to vibration control. Now, I'll not go deeper into this, but just to give you some idea, all of you know that equation of motion of mass in a single degree of freedom damped system of the figure 2.a can be written as mass into acceleration plus damping coefficient into velocity plus stiffness into displacement is equal to the amplitude of the unbalanced force into e to the power j omega t, which can be cos omega t or sin omega t. So we generally work with this. And when we take Fourier transform both the sides, then we can find that x t will be given like this. Okay, where basically what I'm trying to say is that we assume that when force is sinusoidal, the displacement also be sinusoidal, and that sinusoidalness is common e to the power j omega t. Now the force transmitted to the foundation is damping coefficient into velocity plus stiffness into displacement, and then we substitute here like this, and finally we get this. So force transmitted to the foundation is given by stiffness plus j omega damping coefficient against k minus the etc. into this amplitude of the unbalanced force into the sinusoidalness. And then transmissibility is defined as the force that is transmitted to the foundation divided by the force of the unbalanced force. That is this F0 that is main forcing function. And this ratio, you can see it is given like this. So this is what we play with, and from here we learn what to do when we want to control noise or vibration. Now referring to the other figure of where this figure now, that's what I'm talking about. And so there again we write the equation as mx double dot. Now there is no force there, but there is a relative velocity and relative displacement. And this can be rearranged in this form. So this becomes our forcing function now. And again for harmonic excitation, we write our displacement of the foundation y is given as some amplitude. Hello.
कहीं से कहना फोन कर
Shall I continue?
Yes, sir. Please continue, sir. Sorry for that.
Yeah.
Please continue.
Okay. Now for harmonic excitation, we take the displacement of the foundation as some amplitude capital Y again into e to the power j omega t, which can be written as cos omega t plus j omega t. So in other words, it is sinusoidal function. The response will also be harmonic, and that can be written as xt equal to capital X into e to the power j omega t. And then the motion transmissibility, capital X, that is this divided by capital Y from here, that is this, and this again is called transmissibility. We call it motion transmissibility, and that comes out to be this. It may be noted that this equation is exactly the same as we had earlier. That is this one. So force transmissibility was given by this expression, and motion transmissibility is given the same expression. You can see no difference at all, and that's very important, as you will see later. Now this common expression for transmissibility has the following non-dimensional form. We can write like this: transmissibility is equal to this, and now zeta is the damping ratio, that is the damping coefficient divided by critical damping Cc, and this R is the forcing frequency divided by the natural frequency, omega by omega n. And this is again very important, because once we non-dimensionalize, whatever we learn can be generalized, and that's very important. You see here now transmissibility defined in terms of the omega by omega n, and here transmissibility is given by this. Now you can see here it's very interesting. At very low frequencies, it is 10 to the power 0, which is unity. That means whatever force comes on the mass, same thing is transmissibility, or whatever displacement is given to the foundation, same is passed on to the mass. So transmissibility is unity, and therefore that means full force or full motion is being transmitted to the other side. But Now, once you start increasing the frequency, you find that it starts increasing. And when we go to this omega equal to omega n, that means when it is in resonance, so then you find that it tends to infinity. Of course, with damping, it will not go to infinity, but it will be very high all the same. Okay, and then it starts decreasing after that at higher frequencies, and then at sufficiently high frequencies, you can see it comes down to 10 to the power minus 1, which is 0.1. That means 10%. In other words, 90% is the isolation. It's 10% is the transmission. Another thing that you find is very interesting here, that all the time when we design vibration isolators, we'll be working in this region. That means basically we'll be making sure that omega is much greater than omega n. Okay, but mind you, there is a problem here. Omega is not in our hand. Omega is the forcing frequency, and machine speed will tell us what is omega. But natural frequency is in our hand. A designer can make sure that the natural frequency of the system is small, so that this R is much greater than 1. And as you can see here, if it after 3, it comes to almost like 0.1. Another thing is very interesting here. Here we found that when the damping was low, the amplitude was higher and higher, or transmissibility was higher and higher. But here now you find that when damping increases, it is counterproductive. Instead of the transmissibility being very low, it becomes very substantial as we go here. So what I'm trying to tell you is that the lesson that we learned is the damping is very important. Otherwise, we'll have a big problem near resonance. But at the same time, damping should not be too much, because then you will have the problem of, this becoming almost again near unity. Now, this is what I was telling you just now. I'll just repeat here. As frequency ratio tends to unity, transmissibility is inversely proportional to damping ratio zeta. Thus, at around the resonance frequency, in the absence of any damping, transmissibility would tend to infinity. Now, damping plays a crucial role at and around resonance frequency. That means I'm sorry, somebody is speaking in between. Please mute your microphones. However, it is somewhat counterproductive at omega greater than 2 under root omega, and that is what let us take you back. You can see here all these curves are passing through this common point, and that happens to be 2 under root 1.414. So all the time we have to design our systems to make sure that we are on this side of 1.414. And the further we are, better it is. Now that figure also shows that for the force or motion transmissibility to be much less than 1, the frequency ratio must be much more than unity. Now for a lightly damped system, we can prove, from that expression earlier, that transmissibility is approximately given like this. And you can further see if zeta or damping is very small, this will be much less than 1. It becomes 1 by r square. Similarly, the other equation also gives you the same. The motion transmissibility also gives us 1 by r square. So basically what I'm trying to say is we have to make r much greater than 1, so that 1 by r square is much less than 1. And that means the motion transmissibility or force transmissibility both tend to be much less than 1. Now, here I want to tell you the importance of inertia block. Our natural frequency is given like this for when inertia block. Let me just show you first. Next one. Look at this. Now we have machine. What we do is we put the machine on a large mass. We call it inertia block M2, which is M2 is much greater than M1. Often we make it to even more than 3 or preferably even 10. Okay. And this is what is the foundation which we are assuming to be rigid. And then let us see what happens now. So now omega is given by K by total mass M1 plus M2 under root. Now, it follows from those equations that we discussed earlier that in order to reduce the vibration of the machine, as well as to reduce the unbalanced forces transmitted to the foundation, the spring stiffness should be as small as feasible so that the natural frequency of the system is much lower than the excitation frequency. Now, this requirement can also be met by means of inertia block, as I showed you. Now, generally, the inertia block M2 is several times the machine mass M1. Now I really start with the fundamental vibration control, and using those basic things that we just now learned, let's see how we make sure that in industry and various situations we are able to control vibration. Now, just to give you a general idea, a vibration problem generally involves a source of vibration, a dynamical or vibratory system, and finally we want the response which should be minimal. Now, control of vibration therefore consists in modifying the source and or the system. Typical sources of vibration are unbalanced forces and movements in a reciprocating and rotating machinery, turbulent flow in pipes, particularly at the bends and intersections, standing waves like water hammer, etc., and surges. Therefore, vibration control at the source involves balancing of reciprocating and rotating machinery, that is engines, turbines, compressors, blowers, etc. Smoothing of flow in pipes by avoiding separation of boundary layer and proper lubrication of joints, etc. Now, often there is a coupling between vibration and noise. Reducing one would result in reduction of the other. Control of vibration involves proper design of the system or transmission path I repeat this part. Control of vibration involves proper design of the system or transmission path to reduce the vibration of machinery as well as transmissibility of the entire range of speeds and forcing frequencies. Now, what are the requirements of vibration control? Permissible vibration level for each part of a system in a dynamic setting is decided by requirement of functionality or comfort. Now, figure 3.1 that I'm going to show you is representative of the acceptable vibration levels. Vibration control requirement occurs in two classes of vibration: isolation of a sensitive instrument from the support or base motion, and isolation of a support or foundation from the unbalanced force that I showed you in the two figures earlier. The base excitation occurs during vehicle motion over an undulating surface, a satellite launch, and in operation of disk drives. The force transmissibility problem relates to machine mounts and also machine tool vibration, etc. It is generally cost effective to control vibration at the source. Now, this may not be very clearly visible, I don't know, on your screen, but I want to tell you here is that I have given you the constant velocity uh, lines, constant displacement lines, constant acceleration lines. And I just want to tell you here that, uh, just look at this point here. Now, this is where all this, the acceleration, velocity, and displacement of 120 dB, they pass through all of them here. And this corresponds to 1000 radians per second. So here I have frequency in hertz, but just to show you, actually, basically, when converted into radians by multiplying by 2 pi, it becomes 1000 this one. So what I want to tell you here is, I mean, here it is indicated, when it can be destructive, when actual wall damage starts, when cracks can start in the building, or on this side, when, for example, machine vibration is satisfactory, when it starts becoming unsatisfactory, and when it becomes impermissible. Now, this is what I want to tell you. At a frequency of 1000 radians per second, or equivalently 159.15 hertz, three types of vibration level, acceleration level, velocity level, and displacement level are equal to 120 dB. This 120 dB corresponds to the root means square velocity of 1 millimeter per second, or acceleration of 1 meter per second square, and displacement of 1 micrometer. Now, to be acceptable, this is very important for you now, for all of you engineers. To be acceptable, vibration velocity of the machine should be less than 2.15 millimeter per second, or velocity level of 127 dB. And structural damage is likely to occur, or cracks may start appearing when the structure is subjected to seismic acceleration exceeding 0.8 meter per second square. Just a minute. She knows. This is coming in the way. How do I take it to outside? Yeah, thank you. All right. So what I want to tell you was the structural damage is likely to occur, and the cracks may start appearing if the structure is subject to seismic acceleration exceeding 0.8 meter per second square. Now, I told you that vibration can be controlled either at the source or in the path, and there is no third way. Now let us see now what we mean by vibration control at the source. Vibration can be controlled at the source by reducing the excitation. This may be done by reducing the rotational speed of the machine, if possible, without compromising the primary function of the machine. Second is reducing the unbalanced, which in turn may be affected by precise machining of the rotor or crankshaft and selecting a proper configuration. For example, 6-cylinder inline engine is inherently balanced. So we should ask ourselves when we choose this engine whether we can have a 6-cylinder one. If we cannot, then next better is 4. Okay, or on the other side, next better is 8. But 6-cylinder is where all the primary and secondary forces as well as movements are balanced. Now similarly, the flow excitation may be reduced by reducing the flow speed, by reducing the flow, and or increasing the area of cross section of the pipe in which the medium is flowing. Other is smoothing the flow by means of tubular flow straighteners. Those of you who work with turbines, etc., you will realize that in particular for wind tunnels, we make use of these flow straighteners before the flow comes on to the test section, and then streamlining the flow or avoiding the boundary layer separation by means of guide vanes. So this is for the mechanical machinery, and this is for the flow machinery. Now, theory of vibration of single degree of freedom systems has been discussed. That's what we discussed those things earlier. Now, salient conclusions are the same regarding vibration isolation were as follows. For an isolator to yield low transmissibility, the natural frequency of the system should be much less than the forcing frequency, which is often equal to the rotational speed of the machine in corresponding units. A sufficiently low natural frequency can be achieved by means of soft springs and or inertia block. Now, use of inertia block has the additional advantage of limiting the vibration levels of the machine. vibration of the machine and transmissibility at and around the resonance frequency may be controlled by means of damping. And excessive damping could, however, increase transmissibility as I showed you. And viscoelastic elements provide compliance as well as damping. So they are basically very desirable, but we'll go further and see how desirable. Now, we often make use of bonded rubber springs because they give you both the compliance and damping. Natural frequency is inversely proportional to the square root of the static deflection, and the requirement of sufficiently low natural frequency results in large static deflection. Now let me show you the next figure first. Now this is the range of static deflection for different types of isolators. It's a very important design graph. In fact, every mechanical engineer in the industry should have this figure on his desk, because this tells him that when the deflection is very little, then basically you don't get much of vibration isolation. So you start with cork and felt pads, and now that gives that static deflection is in this range, that is less than 0.25 millimeter, and then the natural frequency happens to be between 30 and 100 hertz. And then the next this range, excuse me. Now when we use rubber and elastomers, then this is the range. That means the static deflection lies between around a few millimeter, going down to something like 0.25 millimeter. And that this is where rubber, natural rubber, synthetic rubber, etc., and general elastomers, which may not be necessarily based on rubber. And then you have metal springs. Metal springs come in this range, where the deflection is of this range and corresponding natural frequency is something like a few hertz going down to 2 hertz or so. And finally, the best thing you get here is this, where air springs. Air spring, give you the natural frequency is almost of the between 1 and 3 hertz. And you can see that any machinery, whether it's engine, compressor, fan, typically will be running at as a few hundred RPM. When divided by 60, that will give you around 10. So basically that will be omega is around 10 hertz, and omega natural. And then the natural will be for these air springs will be so small so that the ratio will be large, and when the ratio is large, we get very good vibration isolation. Okay, so this is a very important thing because this gives us the practical side of it, and this gives you the corresponding effect in natural frequency. And let's go back. So this tells us the large static deflection results in mechanical instability. This may be avoided by means of bonded rubber springs. Most anti-vibration mounts in the market make use of these springs. Okay, I repeat this part. Large static deflection results in mechanical instability. So that's not desirable. This may be avoided by means of bonded rubber springs. And most anti-vibration mounts available in the market make use of these springs. Now, as its name suggests, a bonded rubber spring is constructed by bonding the rubber onto metal parts. In fact, one can make use of several of them in series, as I'm going to show you now. And the reason is we want to avoid this. Look at this. I said large static deflection results in mechanical instability. So we really want more deflection. At the same time, we don't want mechanical instability. And what we do is now what I'm going to show you. this one. So you see here, I wanted, you know, large, or thick uh, rubber spring. But then what happens is I'll have mechanical instability. So what I do is I divide those rubber pads into 4 pads of much less, I mean, correspondingly less thickness, and therefore it will be more stable. And in between, we put this thin metal plates. See here. So this is how we are able to get what we want, that is more deflection. At the same time, we make sure that there is no mechanical instability. So this is how we make a composite bonded rubber spring. And now this gives you some idea of the composite bonded rubber springs. Now it may be noted that 4 identical rubber pads that we have just now shown you now, these have been bonded to 5 thin metal plates. Stiffness of such a composite spring in compression will be roughly 1/4 of that of single rubber pad EA by H, where A is area of the cross section of the spring. And to just go back, our H is this. This is H. The same would apply to the spring stiffness in shear. Thus, for the composite rubber spring of that figure, compressive or axial stiffness is given by E, that is, elasticity modulus into area of cross section divided by 4 times the thickness of each of those pads. That is what we call stiffness in axial direction. Then we have torsional or shear stiffness, K sub S, that is now the shear modulus into area of cross section divided by 4H. As I told you, H is the thickness of each of the 4 rubber pads. Now it may be noted that thickness of thin metal plates does not influence the axial as well as shear stiffness of the composite bonded rubber springs shown earlier in figure 3.3, because stiffness of the metallic sheet is higher than that of rubber pad by several orders. So this is very important principle, and therefore in the market, most of the time you have this is what is available, or you get them made also when you want. For example, when I design, uh, anechoic chambers, etc., for industry, I do use this bonded rubber springs to have under the floating floor. Now, when you go to the market and you ask for this anti-vibration mounts, now this is what you get. Typically, it looks like this, and this is how it is put on the surface you want. Now, bonded rubber springs are available in various forms. Each is configured for a particular type of loading. For combined compression and shear loading, one uses anti-vibration mounts shown in this figure. And now our H that I showed earlier, this is what becomes H, and this is the angle alpha, which is very important because otherwise when it is axial, this alpha is 0, but here now alpha is more than 0. So this is, I'm just writing an anti-vibration mount for combined compression and shear. You might ask, when we don't have shear, then what happens? Then we can just use the rubber bonds that I showed you in the previous slide. The anti-vibration mounts of the type of figure 3.4 are used extensively under stationary installations like diesel generators, turbo generators, stationary compressors, etc. Often, several anti-vibration mounts are used in parallel such that their center of buoyancy coincides with the center of gravity. This is very important. Often people make that mistake. So when we use number of AVMs, we must spread them around in such a way that the center of buoyancy works out to be coinciding, more or less coinciding with center of gravity. So this is where you use basically what you people have studied in statics. That is where we find the center of gravity. The same way, the stiffnesses of this can be used to get the center of buoyancy. Now, I told you that, the air springs are the best. And so let us see, that is what is called pneumatic suspension. It has been shown before that for low transmissibility, the natural frequency of the system should be much smaller than the forcing frequency. However, use of springs would result in large static deflection and mechanical instability. Therefore, low frequency isolation is not feasible with metallic springs or viscoelastic pads. Fortunately, pneumatic suspension does not suffer from this weakness. It can yield good isolation with little static deflection even if the forcing frequency tends to zero. Now here is another concept, dynamic vibration absorber. Before I read this, let me show you what it means. You can see here that this is our normal machine, let us say, and then we find that it starts vibrating very heavily or some kind of resonance is occurring. So what we do is we put on that this is what we call dynamic absorber, and it has a mass and a stiffness such that Ka by Ma under root or natural frequency of this should be nearly equal to the natural frequency of the original system. So this is my primary system and this is the auxiliary system which I put on that. So this is what is called dynamic vibration absorbers. A spring mass pair attached to a machine excited at or near its natural frequency as a mechanical appendage so as to absorb its energy is called a dynamic vibration absorber, DVA. Schematic of that I just now showed you in the next figure, and it was invented by Fromm at the beginning of the 20th century, that is about 100 years ago. Its principle may be better understood by making use of electrical analogous electromechanical circuit as I'm going to show you. You see here, when we use electromechanical analogies, a mass is given like this as inline inductance, and stiffness is like a capacitor, and that is here as a shunt element. So Ma is represented as a inline lumped element, and stiffness is represented by a shunt element here. Again, mass is inline, and then it is this. And here, if we take this as rigid, then the velocity will be zero, and this becomes open circuit. But actually, this is where the excitation is coming. So that is V0. So V0 is known to us, and we have to find out what will be V or V1 here, and also VA. But more than that, I want to tell you our main thing is that finally this should not vibrate. So I should design in such a way that this velocity becomes zero. Okay, and let us see now what happens. Now the principle underlying dynamic vibration absorber is this. I just now showed you here that figure 3.8. Their velocity is given as velocity, rate of change of displacement, and d by dt, in the frequency domain can be written as j omega. So in other words, a derivative is equivalent to multiplying by eta into omega. And impedance, I was telling you, Z1 for spring, it is K by J omega. And for mass, Z2 is J omega M. Again, Z3 is stiffness of the absorber divided by J omega. And Z4 is equal to J omega MA. Now in that same figure 3.8b, let's take further. Now you can see here, all of you have some idea of electrical engineering. So you see here that this impedance and this impedance, they are in parallel. Okay, so my total impedance will be Z4 into Z3 divided by Z4 plus Z3. And that's what I'm going to show you here. So Z equivalent becomes Z3 into Z4 by Z3 plus Z4. And then substituting these values, we get this. Now clearly you can see if Ka by Ma, that is Ka Ma, is equal to omega square. Okay, that means the natural frequency square becomes, so this becomes omega square divided by natural frequency square. And if they are equal, that becomes unity, and 1 minus 1 minus 1 is 0, and this tends to infinity. When impedance is infinity, when this impedance becomes infinity, this is like open circuit here, and then velocity becomes 0. That means this mass cannot move at all. It's very interesting. I repeat, when the natural frequency of this is equal to natural frequency of this, then this mass is simply cannot move because it is actually facing infinite impedance. But we should not be very happy about this situation, because then what happens to this V? And you will see what happens. Now this would open up the lower loop I showed you just now. And this is the principle underlying the dynamic vibration absorber. But then the catch is this. Often a DVA is designed to control the resonant vibration of a given machine or rotor or subassembly. Then omega is equal to the forcing frequency is equal to natural frequency, and that equation reduces to VA is equal to V0. So it's very interesting. I mean, though machine is not moving, but our absorber starts moving with this velocity. And if that ma is small, that velocity is even more than the forcing velocity. Okay, so obviously mass of the absorber must be large enough to limit its motion. Otherwise, we would end up transferring the vibration problem from the machine to the DVA mass, which is obviously doesn't mean anything. We have just passed on the problem to other mass. So we have to make sure that this MA is more than M, or at least of the order of M. Now figure 3.8 illustrates the use of a DVA for reducing the velocity transmissibility of a sensitive instrument of mass M. This is what I was telling you, that when we designed this system, we have to make sure this velocity is almost 0. At the same time, this VA is not too much, or let it be equal to V0, but not more than that. Now one should use damping in parallel with spring, or combine the two elements into a viscoelastic element. As a matter of fact, most dynamic absorbers incorporate damping in one way or the other. Now, this is the most important slide from the practical point of view. Figure 3.8 is just a schematic of a dynamic vibration absorber or vibration neutralizer or tuned mass damper. In practice, the primary vibrating system and the dynamic vibration absorber may take a variety of shapes and forms. Some of the well-known applications are actually, this reference is there in the book, so that you are welcome to see there. You can go to that reference for details. Now the so-called stock bridge damper, widely used to reduce wind-induced vibration in the overhead power transmission lines. Second is absorber for high-rise buildings for suppressing primarily the contribution of the first vibration mode in wind-induced oscillations. And pendulum-like DVAs applied to high television towers. And then devices used to stabilize ship roll motion, alternate vibration transmitted from the main rotor to the cockpit of helicopters, improve machine tool operation conditions, reduce the dynamic forces transmitted to an aircraft due to high rates of fire imposed on the cannon motion, Actually, when I say fire, it is basically the force that acts on the machine, your cannon, as a reaction. Control torsional vibration of internal combustion engines and other rotating systems, and attenuate ship roll motion or gyroscopic DV, etc. And another one finally is the centrifugal pendulum vibration absorber. So you can see here it has wide range of applications, but you have to now, mechanical engineer has to apply his mechanical ingenuity along with the basic principles of vibration absorbers. Now I'm going to show you something very basic in this one, and that is what is the principle of impedance mismatch and how does it block transmission of vibration. It has often been observed that unbalanced forces transmitted to the foundation or support structure travel long distance through the structure as structure-bound sound and radiate sound. This is also known as flanking transmission. Therefore, reduction in noise radiation calls for control of unbalanced forces and movements at the source, design of vibration isolators for minimal transmissibility, and blocking transmission of vibration in the support structure by means of impedance mismatch or reflection of power flux and structural damping or absorption or dissipation of power flux. Now this is what all of you use, but you may not have realized how it is uh, working as a vibration absorber. I'm going to talk about viscoelastic interlayer. Now impedance mismatch is often affected by sudden change in characteristic impedance along the transmission path. Common examples of the impedance mismatch are use of gaskets, washers, viscoelastic pads, etc. between two metallic layers or surfaces. The characteristic impedance Y is the product of material mass density rho and sound speed C of a viscoelastic material like rubber is several orders lower than that of a metal. And that is what we mean by impedance mismatch. It can be shown that the dynamic power transmission coefficient across an interface of two materials is given by this, where WT and WI represent the incident power flux and transmitted power flux respectively. Actually, I'm sorry, it's opposite actually. Incident power flux is WI and transmitted this one WT. So this is a typo. Now, yeah, let us first look at this. This is what we mean by impedance mismatch. I have metallic layer and then viscoelastic layer. When I put one over the other, now any power, incident power that was coming through this, they get reflected very substantially and only very little goes further. Same way also, if I put the viscoelastic layer this side and metallic layer this side, and let us say unbalanced forces are coming from this side, again very substantial part of that will be reflected back, because this is the point where impedance is suddenly jumping from very low to very high. Here it was from very high to very low, but the effect is the same, whether low to high or high to low. It is mismatch, and that's what we mean by impedance mismatch. So in order to appreciate that transmission coefficient tau is always less than unity, we may rewrite tau as follows. Actually, let me first take you back. Yeah, you know, this tau is given by this expression, and this thing can be rearranged as 1 minus this. And that you can see here that this tau transmission coefficient will be much less than 1, or if y1 is much less than y2, or y1 is much greater than y2. In both ways, because this is a symmetric function, you will find that in both ways tau will be much less than 1. And that's what is being said here. In other words, transmission of dynamic power across an interface of two materials with vastly different characteristic impedances is very poor. This illustrates the principle and use of impedance mismatch. And the same thing is actually shown here, making use of the conservation of energy or power flux at the interface of two cells. We can see that incident power minus reflected power is equal to transmitted power, or which means transmitted power divided by incident power is given like this, and that reflectivity is given by this. This shows that the effect of the impedance mismatch is to reflect a substantial part of the incident power back to the source. In other words, principle of impedance mismatch is the basis of reflective or reactive dynamical filters. And when I say dynamical filters in mechanical engineering, it can be mechanical vibration isolators. In acoustics, we call them exhaust mufflers or acoustical filters. Now we can also have two impedance mismatches. You can have a metallic layer, another metallic layer. In between you put a gasket. So then we have one impedance mismatch here, another impedance mismatch here. So this is a figure that shows you the use of a viscoelastic layer in between two metallic layers in order to block transmission of vibration or longitudinal waves, to be precise. This arrangement is very common in mechanical engineering practice. All of you use the gaskets, washers all the time. Now it represents a pair of impedance mismatch interfaces A and BB. However, its overall transmission coefficient is not as low as tau square, where tau is the transmission coefficient each of this. In fact, it would be nearly unity except for thick and very compliant interlayers and at high frequencies. This is because the vibrational energy reflected at the interface comes back substantially after reflection. Now let me show you. Let me go back. So you see here, incident power comes here, and then very substantial portion will be reflected back. Very little goes, but what goes here is, again is reflected back because of this one. Comes here, again is reflected back, so it gets entrapped. And that is what causes the problem. Okay, so that's why this interlayer is, not at all very effective. But we'll see how to make it effective. And that is what is done is basically we use damping. I'm going to show you damping treatments for plates and then tell you how we can combine the two. Now, often the sheet metal components generate a lot of noise. For example, the real source of noise in an internal combustion engine is the sharp pressure fluctuations in the cylinder due to combustion. However, most of noise radiation occurs from the sheet metal components like oil pan, valve covers, gear covers, the intake and exhaust manifolds, etc. These components act as mechanical loudspeakers. Excuse me. Now this combustion excited body noise may be reduced either by making these components out of materials with high loss modulus or by means of damping treatments. Now almost all practical damping materials are polymeric plastics or elastomers. In fact, all this can be found in detail in reference 10 in my book. Now, as noise is radiated primarily by flexural vibration, damping treatments or viscoelastic lamina are used for absorbing the energy of flexural waves in thin plates. Damping treatments are two types, free or unconstrained layer damping, that is this, or other one is sandwich or constrained layer damping, that is this. So I repeat here, this is called free layer damping, and this is called constrained layer damping, CLD. In the free layer damping, the flexural wave energy is dissipated through the mechanism of extensional deformation, whereas in the constrained layer damping, the wave energy is dissipated through shear deformation. This is very important, please. Though it doesn't look like, but actually this is what happens here. And shear deformation is what we make use of, and that really takes care of flexural vibrations and therefore the noise. Now, I'll not bother you with the expression, but I just want to tell you the free layer damping treatment often consists of a homogeneous, uniform, adhesive layer of mastic deadener. Its overall loss factor can be calculated like this. But don't worry about that. Let me take you further. And then we find out what is going on in terms of making some approximations, and then we realize that the overall loss factor is only 1/100th of that damping layer inherent one. So what I'm trying to say is, uh, by itself it doesn't look good at all, but in actual practice it's very important. I'll show you. Now typically a constrained layer damping treatment shown in figure sorry, the 3 point this is what I was telling you is free layer damping and this constrained layer damping. So I'm referring to this now. Typically a constrained layer damping treatment shown in that figure is more effective than an FLD treat, that a free layer damping treatment shown in figure A, in that the CLD treatment yields higher composite loss factor with lesser penalty in terms of additional weight. The shear deformation caused in a CLD beam is typically much more than the extensional deformation in an FLD beam. Therefore, the shear damping due to CLD treatment is much more than the extensional damping due to FLD treatment. And now this is what most important thing, all of you please note. A constrained layer damping treatment often consists of a thin, stiff metal foil with a thin adhesive damping layer on one of its sides. This can easily be stuck or pasted onto the base plate to be damped. Now this is available in the market, and one of them you might have heard is triple M, MMM. So that company has all sorts of these damping layers, and with very good glue, etc. And also, of course, you can look at their catalogs and then decide for a particular application what you would like to have. Now, just we are comparing the two treatments, the CLD versus FLD, and the quantitative results presented above are strictly for a simply supported beam. Qualitatively, however, they apply for designing CLD treatments for plates and sheet metal components as well. In particular, now this is very important again from the practical point of view. In particular, near the clamped or fixed edges where the flexural strain is the maximum, CLD treatment will be most effective. I repeat, near the clamped or fixed edges where the flexural strain is the maximum, CLD treatment will be most effective. Now, unlike the free layer damping treatment, the constrained layer damping treatment need not be applied over the entire exposed surface. A modal analysis would help in selective or economic use of CLD treatment, particularly for narrow band excitation. Now, this is where when you come to practice, you do a modal analysis, and then make sure that you put those damping layers, where you have a nodal point, and that nodal points can be found only from the modal analysis. In summary, the CLD treatment yields higher damping and imposes lesser penalty in terms of additional weight as compared to the corresponding free layer damping treatment. So I'll stop here and thank you for your listening, and I'll be very happy to answer any questions that you may be having. And of course, you can ask me even later, because I'll encourage the organizers to let you have a copy of this lecture, and you can then get back to me if you have any doubts.
Now I would like, thank you very much, sir. I would like to request participants to ask questions to Munjal, sir. Is there anybody who needs to interact with sir?
Hello, good morning, sir.
Good morning.
There is too much noise coming. Somebody should.
And anyway, in the meanwhile, can you hear me?
Yeah.
Hello? Yeah, in the meanwhile,
Sir, we can hear you.
let me just tell you something about this book. I have been having what is called this facility for research in technical acoustics for the last 20 years. And this was completely supported by Department of Science and Technology. And it was during the meetings of the steering committee, that I was asked to write a book which people can use, for both teaching and also for using in the industry. And so that is how this book, which was sponsored again by the government, that is the Ministry of Science and Technology. And this book I wrote, and in that I made use of my experience of 4 to 5 decades of consultancy, and I have made sure that there are no derivations at all. All I have given you the ready to use formulae, physical concepts, then solved examples, unsolved exercises. In fact, it is written for the real practicing engineer in mind. And what happened was, this was published by our Indian Institute of Science, IISc Press, in association with what should I say, the World Scientific Publishers in Singapore. And but then, these people, what they did was, they put it at international level, and they made the put the price as $65, 65 US dollars. Now that was too much, because I knew that none of the students in our country would like to have that kind of thing. They'd like to Xerox. Okay, but anyway, so it took me more than 1 year to convince them to bring out an Indian edition. So now Indian edition has been brought out, and it's only 900 rupees. Okay, and also all the books are available at Tata bookstores in our institute, and they give you further 20% discount also. So practically for 700 rupees, you can have this book on your desk all the time, and please feel to use it, and also get back to me if and when you have any doubts. Yeah, now you can ask me your doubts, please.
So I request participants and faculty to raise the questions or ask a question to sir.
Hello, sir.
Yes, please.
Yeah. Tanwal, you can hear you. Please speak.
Hello. Am I audible?
Yes, please.
Yeah. Sir, so my question was from acoustics side. So nowadays, electric vehicles are going to be in demand. So, and for particular two-wheelers, so is there any possibility to enhance their that noise created by electric motor, especially that hissing sound?
Yeah, this is a very practical problem. I mean, I can't answer today, because what I've covered is just the basic fundamentals of it. So I mean, you may contact me later, and then we can
Okay, sir.
really
Okay,
go
sir.
into details.
Okay. And second problem, sir, that one of my students was when he was working in a cement plant. So he
Yeah.
told me that whenever they use exhaust fan, so much dust particles they
Yes.
stick up on the blade. And suppose suddenly that one big piece, like 6 kg piece of that dust suddenly breaks. So that high RPM fan suddenly becomes unbalanced, and sometimes it can damage that structure also. So they have brought some system which will dynamically balance it within a fraction of micro millisecond. So
Yeah.
is it possible? Yeah, we can. Is it in India we have developed such system, or still it is under process? I
You
think
see,
they have many. They have brought. Yeah.
yeah, I have not developed, but let me just tell you, you know, you just get in touch with me. You know, I'm giving you this my email here. Okay. And then
One
I'll let you know the literature where such
okay.
practical problems are discussed. Okay. In fact, you know, there
Yes.
is a book,
Okay.
handbook on the same subject, uh, which has been written, which has been edited by one Professor Crocker in USA. But he has made use of expert knowledge of 165. Sorry, there's a lot of noise coming in. Can you please mute your systems?
Yeah. Hello. Now it's okay, sir.
Yeah, okay. So what I was saying was that hand mic, I'll give you the reference of that book, and that has 165 chapters written by all 165 different experts in the world on various subjects, including everything that you can think of. In fact, I was one of the editors of that book, and in fact, this was edited by 12 persons like me in the world. And so it's a very useful book, just costing about maybe $300. But then, you know, you will have in the industry all problems that you can think of. You know, those practical solutions with all details are discussed there. And each chapter again has a number of references where further details can be found. So what I'm trying to say is practical problems need very practical solutions, and they are you know, they have to be sort of, you know, you have to consult the real experts. Okay, so I can only make sure that I put you on to those experts or the corresponding books. Okay, next please.
Yes, sir.
Sir, book torsional vibrations are also included because you see the problem in the torsional when the system
Yes,
is rotating. So at that time, some torsional vibration and the transmissibility in the cases of torsional vibration absorber and related data can we get from this book? Because one of
yes,
my students is working in
yeah,
this area.
yeah. Not only that, see what happens is that uh, many of the most fundamental part you will get in my book, but then you will for actual this real problems, then references are given at the end of every chapter. Okay, so you can go to
Okay.
that. Okay, so that's what I'm trying to
Sir,
say, that you can use my email, get in touch with me, and I'll be able to help you out.
okay, sir. Sir, one another question. What is high loss modulus? I think you talk about
Yes,
that to
yes,
reduce. So exactly what is meaning of sir high loss
yeah,
modulus?
yeah. You know that basically we write, you know, stress divided by strain as elastic modulus, right? Okay.
Okay.
Now this elastic modulus in real practice is not constant. It's a function
Yeah.
of frequency, because
Okay.
basically the damping inside is a function of frequency. So what happens is then E, but because for any given stress, the strain will be complex, or vice versa. For a given strain, stress will be complex. So net
Right.
result is the stress divided by strain becomes complex. So we say that elastic modulus is complex. It has a real part, and the real part is called storage modulus, and
Right.
imaginary part is called loss modulus. Okay,
Mm.
so this is what I
Okay.
meant, that, you know, when we want damping in the system, we want to make sure the loss modulus should be high, and particularly it
Okay.
should be high at the frequencies which we have in mind. Okay, so that's why a
Yeah.
material that is good for something, one application, it may not be so that good for another application. And all those things are given in those my book also, and I'll further in the references details are given. In fact, there are books fully on damping materials, so I'll be able
Okay.
to help you out. You just write to me and I'll tell you that.
Okay, sir.
Okay.
I will try. Okay, I will try.
Next, please.
Sir, myself SS Pathan. My question is that you are talking about CLD and FLDs.
Yes.
So in some situations where actually FLD and CLD are not applicable, such as in high temperature applications. So
Yes.
how can we, what are the ways of improving damping?
Yes. In fact, I made one statement. Maybe I'll repeat that part, and that was that you have in the market the damping tapes available. Okay, so it has glue on one side. Okay, and so you just remove that part, that one glue, put that glue on that machine or the part that you want to damp, and that makes it a CLD system, because you have your mass, over that comes the glue part, which is actually that is the real damping layer, and then comes the other thin metallic part on this one. So this is what I was telling you, that if you look at the literature of these companies, and one typical company I gave you was this Triple M. Okay, and they, if you go to their literature, they have, I would not say thousands, but at least hundreds types of tapes, and those some of those tapes will also tell you that you can use even at high temperature, because you are talking of high temperature. So that glue can stand a high temperature. It will not lose its damping properties. Also, it will not lose its glue properties. So that's what I'm trying to tell you. Taking into account all such situations, these companies have now developed damping materials, and complete company runs only on damping materials. Okay, so all you have to do is look at those catalogs and then get in touch with them, and they'll be able to supply you exactly what you want. Okay.
Thank you so much. Thank you, sir.
You're welcome.
Okay. Any other question from the participants? Okay. So I think there are no. Yes, please.
Yes, sir.
Yes, please.
I have a question to ask you. So you must be knowing predictive maintenance of compressor. The people have started using Industry 4.0 predictive maintenance state.
Yes.
People are using the reactive maintenance or preventive maintenance, or maybe they have started using conditional based monitoring. Now,
Yes.
in Industry 4.0, they are talking about the PDM, that is the predictive maintenance, data analytics, and all. So my question is, suppose we want to apply the strategy of PDM, predictive maintenance, to the compressors, big compressors.
Yes.
How vibration control or how vibration monitoring or analysis will help us in PDM?
Yeah, what happens is that you have has to be made sure right at the point when you're ordering that system. Okay, that company has to tell you if that compressor is running very nicely. Okay, then what would be the typical vibration levels at the bearings, etc. Okay,
sir.
And then you in fact, when they supply to you the system, the sensors will already be there, and they should never be removed. And all the time, those sensors will be telling you the vibration at those points. And this vibration will be fed onto an analyzer, which automatically tells you at what point or which day suddenly it will give you a warning that vibration at the, for example, outer race of a bearing or inner race, it has become more than what it should be, telling you that there's potentially a problem, some malfunction there.
Yes, sir.
So you immediately, it will, that system, preventive maintenance system, which is supplied along with the compressor, that will also tell you where exactly you go, look at that point and then you go to that, and then again you will have help on the software that's supplied with it, and that will tell you what you should do. Okay, everything will be, you will be completely guided by that preventive maintenance system that has been supplied along with a compressor. So you have to make sure that when you buy some machine which you cannot afford to do without, so then you make sure that that system is supplied with it, and person who runs compressor, he'll train properly to look at those warning signals and then do the preventive maintenance. So all that is these days very nicely taken care of by the supplier of the system itself.
So, sir, I have observed that the people are giving about the preventive maintenance and maybe condition-based monitoring. Means what exactly the condition of vibrations
Yeah,
are not.
this is what I meant by when I said condition deteriorates. That means vibration level will start increasing at that point, or temperature will start increasing. So temperature pickup or vibration pickup, they will warn the system, and system will in turn send the warning to you. Anybody sitting on the computer will get those red signals coming, and then help system thing will also come in there. It will also immediately tell you to stop the machine and open up that bearing and then do whatever do. I mean, everything, all the advice will be there in that for preventive maintenance, and that's what is called condition-based maintenance.
Yes, sir. Thank you very much, sir. Over to Rita.
Welcome. Welcome.
Okay. Is there any other question?
Okay.
Yeah. So shall we call it a day?
Yeah, sir. Yes, I think there is no questions. So before we end the sessions, I would like to share my word of thanks to all of the persons who have made this event possible and successful. So good morning all. Yeah, it's given me immense pleasure to deliver the word of thanks for this talk. For delivering full talk on control. Personally, I have enjoyed a lot because being an instrumentation and control engineer. We are very much thankful to our principal, Dr. Rajul Gajjar and Professor R.B. Khasya for the guidance and support to organize this talk. A special thanks to AICTE Delhi for giving us a chance to interact with such a person. I'm very much thankful to our team, Dr. Bhami Sedani sir, Dr. Pivita sir, Dr. R.M. Yadav, Professor Bhavin Mehta, and Professor Lalit Patel, and our HOD, Dr. N.M. for their sincere efforts to make this talk possible. And finally, I would like to express sincere gratitude to respected HODs, faculty members, students, and participants for making this talk a grand success. Thank you all. And Munjal sir, we are looking forward to have you in our college for offline talk maybe next month.
Hopefully, yeah, things will improve, by the end of the year. So I'll start visiting the colleges, and then we'll meet.
Yeah. So thank you very much, sir. So we call it a day for. Thank you.
Okay.
Bye.
Thank you.
Have a good day to all.
Bye bye.
Bye, sir.